This is CS350. I'm Karthik Gopalan, and today we will talk about processes. Processes are a very central concept in operating systems. Everything that an operating system does is in one way or another related to some kind of service that the operating system provides to processes. So everything the operating system does is usually for processes. So let's see what processes are. Informally, a process is defined as a program in execution. What this means is, let's say that you compile a C program and you get a binary file, a binary executable file. As long as the executable is stored on the disk, you cannot do anything with it. It's a passive entity sitting on the disk, just a set of instructions. In order to do something with an executable binary, you need to run it. Once you execute it, then the binary file gives rise to a process. Essentially, that's what we mean by a process being a program in execution. Program is a binary executable file, whereas a process is an active entity that executes the instructions in the programs. So process is not the same as a program. It is more than just a program. Program is a passive entity, process is an actively executing entity. So program or the executable code or instructions, that's just one part of the process. So what else constitutes a process? We'll see in the next slide. So a process has a lot of different components. So some of the most prominent components or the most important components of a process are the memory, its procedure call stack, and the set of registers and counters that are associated with the process. Memory, as we all know, stores the code and the data associated with the process. Memory can either be statically allocated memory, which means that the memory is allocated at the time that the process starts running. Or it could be dynamically allocated memory, which means that the process has to explicitly request for additional memory from the operating system. The procedure called stack is basically a stack, as the name suggests, where the function, whenever you invoke a function call, then the function arguments, the return values, the return address, all these are stored in a stack frame, and the stack frame is popped into the stack. We will soon take a look at where exactly the procedure call stack is located. Again, procedure call stack is technically part of the memory address space of the process. There are various CPU registers that a process uses during its execution, such as a program counter, which keeps track of which instruction you are executing at any point in time. Then a stack pointer, which keeps track of the most recent stack frame or the information about the most recent function call. And then there are various general purpose registers that a process may be using. There may also be performance counters associated with the process. All this is part of the process state. As you can see, it's not just the executable code, but all the data, information about the process execution at any point in time. All this is part of the process state. In addition, there is also state that's maintained by the operating system on behalf of each process. For example, if a process opens certain files, then internally the operating system would maintain information such as what's the file name, what's the file descriptor, in what mode was the file opened. If, for example, a process opens a network connection, for example, a TCP connection to communicate with another computer over the network, then the information about that network connection may be stored inside the operating system. So a lot of such internal state that's associated with the process is also part of the process state. Um, so we are not, so this is not an exhaustive list. The specific details of what constitutes a process state varies from one operating system to another, But in general, certainly memory, registers, file descriptors, socket descriptors, these are all part of a process state. Next, let's take a look at how the memory of a process is laid out. So in this picture, we show the memory layout of a single process. So a single process runs and as it executes various instructions, it accesses its memory. The memory address space of a process typically has the format shown in this slide. Again, the details vary from operating system to operating system, but generally all processes have a text area which refers to the executable instructions. And then there is statically assigned data which is allocated at the time the process starts running. These statically allocated data may include things like global variables, constants, and so forth. Um, then there is heap, which refers to dynamically allocated memory. Whenever you perform a malloc operation in a C program, then you're essentially allocating memory on the heap. If you do more malloc operations, the memory would be, the size of the heap would increase. Um, and typically when you free, when you call the corresponding free operation, the size of the heap doesn't automatically decrease. Rather, the memory is kept around for reuse by future malloc operations. And when the process dies, all the memory is released back to the operating system. And then the final component shown here is the stack. Stack, as you can see, it grows from the from the top of the address space towards the heap. That way, the gap between the heap and the stack can be used by either the stack or the heap. So you don't have any hard limit on the size to which a heap can grow. And the address space of a process is used very efficiently. Now with 64-bit architectures, the address space of a process can be very large. The max shown in this picture could be as large as 2 to the power of 64 bytes, which makes it really moot whether we use the space in the gap efficiently or not. Um, but for legacy systems such as 16-bit or even 32-bit architectures, it was important to use the address space efficiently. Hence, the operating system designers allowed the heap and the stack to grow towards each other. Another point to note here is that the address space range shown here from 0 to max represents the virtual address space of a process, which means that the process's view of its own memory, which is different from the actual physical memory in the system. A process thinks that it has memory from 0 to max bytes that it can access any way it wants. However, the operating system may be managing many processes, each of which has the ability to access the address space from 0 to max. So it becomes the job of the operating system to shuffle the virtual address space of each process on the physical memory. What this means is that the virtual address space of a given process has to be mapped to the physical address space. There is a translation from virtual address space of a process to the physical memory of the computer. And it becomes the job of the operating system and some additional hardware in the CPU to perform this translation. We will have a separate lecture on how the virtual memory management system works. It's a very important part of the operating system, but the thing to just note here or remember here is that 0 to max is not the entire memory of the computer. It's the view of the memory seen by a single process. Now, let's look at some very simple ways in which the physical memory of a computer could be managed. In this picture, the figure A here shows an operating system which occupies the lowest parts of the physical memory. from 0 to a certain limit. This consists of operating system code, data, and so forth. Usually the operating system's memory is protected from access by other regular programs in the system. There is a privilege and protection mechanism imposed by both the hardware and the software that we will learn about later in this course. The regular user programs are loaded into some part of the main memory. Again, in this particular figure, we see two processes running in the main memory. There is a base and a limit associated with the memory of each process. So the base address represents where the process's memory allocation begins, and the limit represents where it ends. If a process tries to access memory that's beyond its limit, then the operating system would generate an error or an exception. So, so that way you can ensure that one process doesn't access the memory that belongs to another process. Usually this type of protection is enforced by a combination of hardware and software mechanisms. Now, again, remember that this is a very simplistic representation of memory allocation for a process. In reality, a process may not have a continuous chunk of memory allocated for it in the physical memory. Rather, its memory may be split up all over the physical memory, and then the virtual memory management system that we discussed in the previous slide would take care of mapping a process virtual memory to physical memory. Figure B shows uh, two processes that are using the same binary executable. You can take a single binary program and execute it twice, in which case you get two processes, processes 1 and 2. So figure B here shows that the two processes are using the same program. So the operating system loads the program only once into the main memory and then allows each process to have its own data heap, stack, and so forth. So this way operating system uses the memory more efficiently because the executable code is loaded into the main memory only once, whereas it can be used multiple times by different processes. So how do you create a process? A process is created using the fork system call. Fork system call is a very simple system call that allows the entire state of a process to be duplicated. Now, this may not sound like a very useful thing to do to duplicate an existing process, but we will soon see how this duplication functionality can be used to do very interesting things. When do you create a process? There are various ways in which you can create a process. One is when you run a program at the command line. Normally in a shell we would type a command and the program runs. What this means is that you are creating a process, or rather the shell in which you type the command invokes fork system call, which then creates the process and runs the command that you execute. In addition, operating system by itself can also create processes. Normally when the operating system boots up, then at that time the init process would start a bunch of services that keep running for the entire duration uh, uh, of of the lifetime of the operating system. So uh, eh, various processes are created and terminated by the operating system throughout the lifetime of the system. Finally, in all cases, whether you start a process through command line or as a boot time service or through any other means, the basic mechanism is to use the fork system call, which means that one process starts, invokes, or creates another process. So let's take a look at how the fork system call works. Here is an example code in which we show how a fork system call can be used to create another process. This is a very simple system call. Again, the exact code is available on the course website, and I encourage you to try out the code on your lab computers or on your own laptop. This code snippet here shows that an existing process, which we call the parent process, it would invoke the fork system call. Fork takes no arguments and it returns back an integer value which represents the process ID of the newly created process. Now, fork is a very interesting system call. Remember that normally you would invoke a function call or any other system call once. You would invoke it once and then the function call would return once, back to the caller. In fork is special in the sense that fork is invoked once, but it will return twice. Why? Because remember that fork is its job is to create a new process. And once a new process is created, the new process starts off at the exact uh, location or the exact instruction that follows fork. So both the parent process and the newly created child process would start from the if statement once fork returns. Thus, fork is called once by the parent process, but it returns twice, once in the parent process and once in the child process. After returning from fork, both the child and the parent are doing the exact same thing. They are executing the statement which corresponds to the if statement in this example. Both of them check if there was an error. Of course, if fork executed successfully, then there would be no error. However, if there was an error, then the parent process would notice that a negative value was returned and you would handle the error appropriately. If everything goes well, then both the parent and the child move on to the second if condition. Here, here's where things get interesting. Now, the return value of fork is different in the parent and the child. This is so that we can distinguish between the parent and the child process and do different things in the parent and the child. So if uh, you are returning from fork in the parent, then the return value would be non-zero or positive. And if you're returning back in the child process, then the return value would be 0. In the parent process, the return value represents the process ID of the child. Every process has a unique identifier associated by the operating system. So fork returns the identity of the child to the parent process. So at the second if condition, we check if the process ID or the return value of fork equals 0. If so, this is the child process, and in the if second if block, you can execute code that should be executed by the child process. On the other hand, this condition check would fail for the parent because the return value was non-zero. So the parent would go to the third if block and execute the code there because the corresponding condition check would succeed. So in this example, the child prints the statement this is the child and exits, whereas the parent prints this is the parent and it also prints the process ID of the child and then it exits. So as you can see in this very simple example, we have a parent process has created a child process. The child process prints one statement, whereas parent process prints another statement. And of course, you can replace this print statements by any complicated computation that you want to execute. So to summarize the discussion, fork is a special system call used to create a new process. It is called once, but it returns twice, once in the parent and once in the child. The parent and the child are two different processes. Although at the time of creation, the child process is an exact replica of the parent process, but they are still two different processes with their own memory address spaces. How do you make the child process do something different? You have to check the return value of the fork. If the return value is 0, then it's the child process. If the return value is non-zero, then it's the parent process. And correspondingly, you do different tasks in the parent and the child. Now that we know how the fork system call works, we are ready to understand the notion of a process hierarchy tree. What this means is that every process has a parent process, and if it uses a fork system call, it would have a child process. At the top of the hierarchy tree is the initial process that is started by the operating system. Usually this is called the init process. In this example, we have process A, which has two child processes B and C, and then B has three child processes D, E, and F. Processes at the same level are called siblings. Processes that are derived from the same parent rather are called siblings. So B and C are siblings, and D, E, and F are siblings. Uh, so A is the parent of B, and A is the parent of C, B is the parent of D, E, and F. You also have other intuitive terminologies. For example, you could say that A is an ancestor of D, E, and F, and D, E, and F are correspondingly descendants of A. But remember that all of these processes are independent processes. There is a hierarchical relationship, and there are certain things that a parent process can do with a child process. But in general, once you create a process, the process is pretty much an independent process with its own address space and its own execution context. So next, let's take a look at how several processes share the computing resources on a system. Uh, by now we have the general idea that you can have many processes running simultaneously or concurrently on a given computer, and there may be only a limited number of CPUs. Assume for now that you have only one CPU on your computer. So then the question becomes, how can many processes share a single CPU? There has to be some sort of intervention from the operating system so that you can decide who gets to run on the CPU, how long does a process gets to run on the CPU, and when does a process get to run on the CPU. Now there is a specific component in the operating system, this is called the CPU scheduler, which decides these questions. Uh, which decides how does the control of the CPU get transferred between different processes. Any process which is ready to do some useful computation, it is placed in a ready queue or a queue of ready processes. The CPU scheduler, the logic for the CPU scheduler decides who goes next, who gets control of the CPU next. So there are actually two components in this decision process. First is of course deciding who goes next, but then the next is taking that process's execution state and installing it on the CPU. For example, its registers, program counter, and so on, the memory, virtual memory translation state. So all this information has to be installed on the CPU and the process has to be resumed. So, so the first part, which is deciding or picking the process that will execute on the CPU, this is the actual CPU scheduler. Whereas the task of installing the process state on the CPU, that's called dispatching. So scheduling and dispatching are technically two different components, but they are normally combined into one generic term called CPU scheduler by when people talk about the scheduling process. So so we will talk about the specific algorithms for CPU scheduling at some later point. Just one thing to keep in mind is that the queue of ready processes is not a first in first out. It could be first in first out, but it doesn't have to be first in first out. The CPU scheduler can implement any policy to pick the next process. It could pick the process which will take the least amount of time, which is called shortest job first, or it could pick a process which is the most important process, priority scheduling, or it could just cycle through all the processes for fixed amounts of time, for example round robin. So there are various algorithms by which a CPU scheduler can decide who goes next. It doesn't have to be strictly in a first in first out order. This brings us to the concept of process life cycle. This is a very important concept to understand clearly. What this shows is the various states through which a process goes as it is executing on the system. When a process has something useful to do, it is placed in a ready queue, as we saw in the previous slide. This corresponds to the ready state. When a process is in a ready state, it means that it is ready to do something useful, but it doesn't yet have control of the CPU. So it's waiting for the CPU scheduler to pick it up and schedule it on the CPU. So when a CPU scheduler picks up a process and gives it control of the CPU, the process transitions from the ready state to the running state. This is shown by transition number 3 in the slide. The process can run on the CPU, that is execute instructions one at a time in the running state. So during the running state, a process has active control of the CPU. At some point, a process may decide to give up the CPU voluntarily. For example, a process may want to perform certain I/O operations. So in order to wait for the I/O operation, it may take a long time for the I/O operation to complete. So during this time, instead of hogging the CPU, the process can give up the CPU. And the process moves from running state to blocked state. So this is shown by transition number 1 in the slide. When a process is in blocked state, it is waiting for some event to occur. Once the event occurs, then the process can move back to ready state, which is shown by transition number 4. In ready state, again, it can wait for the CPU scheduler to pick it up, then move to running state, and then at some point to blocked state, and so forth. So most of the time, processes are going through this cycle from ready to running, running to blocked, blocked to ready, and back again. Now, occasionally, you would also see that there is another transition, which is labeled transition number 2, which goes from running state to ready state. What this means is that the process was doing something useful on the CPU, but the CPU scheduler decided that somebody else needs the CPU. So the process was taken out of the CPU and put back in the ready queue. This usually happens when a process runs on the CPU for too long. So it means that the process exhausted its quota of CPU cycles, and then the operating system decided that this process has to go back to ready queue so somebody else can get a chance. So this is called preemption. Preemption means to force a process to give up the CPU, and this is represented by transition number 2. Preemption usually happens for CPU intensive processes. What that means is that a process runs on the CPU for too long, and as a result, the CPU scheduler preempts the process, and the process goes back to ready queue. So this is the general process life cycle, and it's important to understand these various states because they have implications throughout throughout every other component of the system. This slide here shows a typical process state, typical kernel level data structures that are maintained for each process. Now you don't have to memorize everything, but just remember that the main component. So for example, in the process management context, you have registers, program counters, stack pointer, the privilege level, and so on. In the memory management context, you have the code segment, data segment, stack segment, etc. Similarly, for the file management, you have open files, open sockets, user IDs, and so on. So everything together constitutes a process state. Now, if you are interested in seeing the process state maintained by the Linux operating system, you can do so by visiting the website shown in this slide and then searching for the data structure task underscore struct. This is a very comprehensive structure maintained by Linux, which is also makes for an interesting reading, that you can go through the various fields and see whether you can relate to some of the concepts you have already learned in the class. For example, can you locate the process ID in Linux? Can you locate um, the memory management context in Linux, or the file descriptor table in Linux. And all these you can find directly through the task structure. There are various ways you can examine processes in a Unix or generally a Linux system. For example, you can use a command line uh, command called PS. PS gives you the state of a process. There are various arguments you can give to PS to get more information. Generally, if you use PS minus ELF, then it gives you detailed information about a process. There are also other ways to get information about a process. /proc directory in Linux has a subdirectory for every active process, and within that subdirectory you can find very interesting information. For example, the memory used by the process, and all other types of statistics. Finally, the top command is a more dynamic gives a more dynamic view of the process state in the system, listing of processes, and you can sort processes by CPU usage, memory usage. You can send signals to processes and so on. So I would encourage you to try out these commands, or search through the /proc directory when you get a chance. Next, we will take a look at the exec system call, which allows a process to execute a completely new executable file. Uh, so, for example, let's say you consider how a shell executes a command. On a command line, you type the command, and the typed command runs. So for example, if you type pwd, then the shell will go and find the binary file corresponding to pwd, and it will run that program and print the output. So how did that work? There was fork involved because the shell had to fork a new process, but there was also another system call involved called the exec system call. So the shell forks the child process. The child process finds the binary file /bin pwd, and then calls exec to execute that binary file. So the purpose of exec is to replace the current process's memory with a new image. What that means is that all the existing memory of a process is overwritten by the memory image of the new program that you want to execute. To illustrate this, if you take a look at this picture, the parent process first forks a child process, the child process then calls exec, and then the child process image is replaced by a new program image. So the new program image completely overwrites whatever was there in the child process. This may look a little bit inefficient. Why should you fork first and then exec? Why not just exec directly? Right? Sometimes you want to keep the parent process around so that the parent process can do other things. For example, in the previous slide, we saw a shell process that forked the child process, and then it waited for the child process to finish, and then the shell was ready to do other things. So similarly, you want to keep the parent around. So in this case, so hence that's why we do fork first and then exec. If you did exec directly, then you would completely lose the parent process's image. So then the other question is, why have two steps, fork and exec? Fork, as we all know, it creates a replica of the parent process, which seems pretty wasteful because you're going to replace the child process image with a completely new image. So it turns out that operating system designers have thought about this problem. If you directly duplicate the parent process in the child, then it will be a lot of effort. Rather, the operating systems use a lazy approach. They do not immediately copy the memory of the parent process. When a child is created, uh, no memory is copied unless the child tries to write to a piece of memory that it inherits from the parent. So this mechanism is called copy on write. Where with the copy on write mechanism, you can delay copying pages from the parent till you actually need to. So as far as the exec system call is concerned, what this means is that if the parent forks a child process and the child executes exec right away, then there is no overhead. There was no copying of memory from parents, and you created a new program image without the overhead of copying. So this type of optimization is common in almost all modern operating systems. So the use of fork and exec really doesn't introduce significant overhead. This example shows how an exec system call can be used. Here a parent process forks a child process, and if the fork operation succeeds, then the child process executes the code in the second if block. The child process executes a system call called exec lp, and here there are a bunch of arguments that may seem very complicated, but actually it's very simple. We are executing a binary file called echo. The exec lp system call automatically figures out the path of the binary file, and executes and loads the file. We are also passing a bunch of arguments. So you will see that the word echo is repeated twice. The second repetition is the command line argument for the echo program, which is argv0. If you are writing a C program and reading command lines, that would be argv0 in the main function. Then the third argument is the argument given to echo program hello from the child, and the last argument null basically represent a termination of the arguments list. So the exec system call here takes variable list of arguments, and if exec succeeds, then something very interesting happens. uh, Remember that with fork system call you called it once and it returned twice. Exec is also interesting. Now you call exec system call once and it doesn't return. If exec is successful, it will not return. The only condition under which exec will return back is if there was an error. So in this code, you will notice that the statement following the if statement is an exit statement with an error code of 2, exit 2. What this means is that if exec returned, then it means something went wrong. For example, you could not load the binary file, or there was something wrong with the arguments and so on. So uh, if everything goes fine and exec succeeds, then exec will not return. All the code that you see on this slide would be replaced in the child process with the code for the exec program. On the other hand, you can see that the parent process carries on doing whatever it's supposed to do after forking the child process. So in summary, the exec system call replaces the calling program's image with a new program image. And there is also another interesting property of exec. If you had certain files that were open in the process before exec was called, then those files will remain open in the exact program image, in the new program image. Now, this may seem very strange, but remember that the file descriptor state, or even say the socket descriptor state, it's maintained by the operating system. So it's not part of the memory image, and operating system keeps these descriptors open to enable certain useful functionality. When we look at inter-process communication, we will see how pipes can be used to redirect the output of one process into another process. So just keep this property in mind as we go forward, that after an exec operation, not everything in the original process is replaced with a new program image. The file descriptors that were opened before would remain open in the new child process, new program image, so that they can be used in some manner by the new image. So here's a listing of various number of variants of the exec system call. Uh, Again, you don't have to memorize everything. Normally, you can just look up the man pages and pick the version of exec system call that's most useful. In the example, we used exec lp, but if you're writing something like a shell program, then you might find it more useful to use the exec v or exec vp versions of the system call, because that way you can pack all the arguments in a char star array, and then traverse through the array as you need to. Next, we look at the wait system call, which allows a parent process to monitor the child process's completion. What this means is that after a parent process creates a child, it might want to know when the child process terminates. For example, a shell might launch a command, and then the shell may wait for the command to finish before executing another command. So in this case, the parent process, the shell, has to wait for the child process to complete. This is accomplished through the wait system call. The parent process can call the wait system call. Once the child terminates, the wait system call can return back with information about how the child process completed. Let's take a look at an example. In this slide, we have a piece of code where a parent process forks a child process. The child process executes the exec system call. In this case, it's trying to print a file using the lpr command, but that's kind of irrelevant to the actual point of this slide. The parent process, if you notice in the else block, the parent process invokes a version of a wait system call called wait PID. So wait PID allows the parent process to wait for a specific process, a specific child process, whereas the generic wait system call allows a parent to wait for any of its child processes to terminate. So one of the arguments for wait PID system call is a status, which is passed by reference. So when the child process terminates, we have seen before that the exit system call can be used to return a status back to the parent. So that exit status of the child would be copied into the status argument when the wait system call returns back to the parent. So the parent can retrieve the exit status of the child through the second argument of the wait PID system call. So alternatively, you could also use a more complicated while loop shown in comments here if you want to use the generic wait system call. So if you want to wait for a specific process, you can either use wait PID or you could use a while loop. There are a couple of other system calls that you might find useful. If you want a process to sleep or pause its execution for a certain amount of time, you can use the sleep system call, which would uh, pause the execution of the process for the specified number of seconds. There are also finer granularity versions of this system call. For example, usleep would allow you to allow a process to sleep for microseconds, and nanosleep would allow a process to sleep for nanoseconds, provided that the underlying hardware supports that kind of timer granularity. Then there is the exit system call, which we saw earlier, which allows a process to terminate explicitly with some sort of a exit status. For example, if a process terminates normally, then it would exit with status 0. Or if a process wants to terminate with an error, it could return a non-zero exit value. Orphan processes are processes that whose parent processes have died. In this case, these processes are inherited by the init process in the system. Init process is the original process that starts after boot, after the system boots up. So orphan processes have a parent process ID of 1. And there is an example shown here where an orphan process is created. Be sure that if you run this code, then you kill the orphan process after you're done with the example. Uh, then there is another terminology that of called zombie processes. Here, unlike orphan process, here we have a case where the child process has died and the parent process has not yet called wait system call. Normally, parent processes are expected to call the wait or wait PID system call to retrieve the status of the child. So since the parent process may request the status of the child any time in the future, the operating system keeps the exit status around. The child process itself dies. It's all its memory state and any other operating system state is released. So there is really no resources being used in the operating system. A zombie process is effectively just an integer value, exit status value, sitting in the operating system's process table. So once a parent process calls wait, then the state of the zombie process is cleared up. So so other than that, zombie process don't impose any overhead on the system. These are some of the references for the material covered in this lecture. They have been taken from various sources, but primarily the material in chapter 2 of Tenenbaum's book and various man pages would be very useful. Uh, and also you can take a look at the Linux source code if you're interested to see how the task struct is organized and what are the various fields in it. That brings us to the end of the topic of processes.